Okay, well, welcome everyone to another TCS Plus talk. Today we're very lucky to have Shay Moran from the Technion and Google Research, who will tell us about a characterization of multi-class PAC learning. So just before we get started, I just want to say that we're always looking for people's suggestions for talks that you think would be great for TCS Plus. And I also want to encourage everyone to keep their cameras on and give Shay a little bit of visual feedback from the audience. And after the talk, we can stay, the call stays open, we'll hang out, we'll ask questions. And then the talk is being recorded and I'll post it on YouTube. But I think that gets all the administrative things out of the way. So Shay, please take it away.
Okay, yes, so thanks, Eric, and I want to thank the organizers who are not with us online for inviting me. Yes, and let me reiterate that I'll be happy if everyone can maybe leave their camera on and ask questions, and yeah, any feedback will be greatly appreciated. Hi, Sumega. Okay, so yeah, so I'll be talking on a joint work with Nathalie Bouchim, who is here with us, and she's also on the job market, with Daniel Carmon, Irid Dinur, and Amiri Udayov. And this is a work about PAC learning in the multi-class setting. So I will soon explain what it is. Okay, it will be presented in stock in a few weeks, or was it Fox? Fox maybe. Okay, so I'll begin with some background so that everything will be self-contained. Like you don't need to have any background in learning theory, although if you do have, it's helpful. So I'll first tell you a little bit about binary classification, which is the traditional setting. And in this setting, we more or less know everything. And then I'll talk about multiclass classification, give you some background what was known before our work, and then I'll tell you about our work. And as I said, please ask questions. If anything is unclear, please ask me. Okay, great. So so let's begin with binary classification. So the inspiration, what we want to model is classification tasks. So you can example that our learning algorithm it needs to learn how to classify images of cats from images of dogs. As a training set, it gets a sequence of images with labels. So we tell the algorithm what is a dog and what is a cat. And then we ask it to correctly classify a new example that it hasn't seen. Okay, so, and of course, we want it to classify correctly. And the way we will model these learning tasks is using the PAC learning setting, which was discovered independently in the East and the West by Valiant in the West and by Chavonenkis and Vapnik in the East. Okay, so the game is like this. So the learning algorithm receives as an input a training set of examples. So every example is an instance in the label. And they are drawn, we assume in these settings that they are drawn IID from some distribution P over the domain. And they are labeled by some H star, by some labeling function that we denote by H star. And then there is one more example that is being sampled, an unlabeled example, just X. And the goal is to guess correctly, to predict correctly the label of X. What is H star of X? Okay, and in the PAC learning setting, we assume that the target function H star, which we don't know what it is coming from a known class of functions. So capital H is a known class of functions, but H star is not known. All we know is that it is from the class. And also the distribution P over the domain from which we get the examples is also unknown. Okay, good. So for example, H can be the class of half planes in the plane, and maybe H star is this half plane. So on the left side it is negative labels, and and here is positive labels. And maybe the training set looks like that, right? So we have like 10 examples or 11 examples, 12 examples, and then we get a new test point, and we need to correctly classify it. So here it's pretty convenient. Here we will just classify it as minus, because if it would be a plus, then the pluses wouldn't be separated from the minuses. The convex hull of the pluses would intersect the convex hull of the minuses. So this is a very convenient question. We know the answer. We know it's a minus. But it could also be that the test point would be sampled here, in which it is less clear how to answer. It can be both plus and minus, and we need to make some smart decision rule. Okay, so the observation is that always a random guess of the label, right? We can just toss a coin and randomly guess the label, and then our error will be exactly 1/2. And the question is for which classes H, the guiding question is for which classes H can we do better? For example, whether for half planes we can do better. And this drives the definition of PAC learnability. So we say that a class H is PAC learnable if we have there is a vanishing bound on the arrow. So we have some vanishing bound on the arrow that goes to 0. And we also have a learning rule such that if the learning rule play this game, so it is being sampled M training examples and 1 test example, then the probability that it will misclassify the test example will be at most R of M. So it goes to 0 as M goes to infinity. Okay, that's the game, and that's the definition. And let me just stress one property of this definition is that it is distribution free. What does this mean, that it is distribution free? It means that this rate R of M applies uniformly to all distributions P and all target functions H star. You could consider other definitions where you still have the same learning rule, but every different distribution and target function, you have a different rate that goes to 0. This is also this also makes sense, but it's not the case here. That's how PAC learning is defined. Any questions? Okay, great. So now a basic question is, once we have such a definition of PAC learnability, the basic question is which hypothesis classes, which function classes are learnable, and also how do we learn them once they are learnable? What are the algorithmic principles of learning? So this question has been studied and more or less fully answered. And the main theorem in this context is called the fundamental theorem of PAC learning. Again, it was proven both in the East and the West. And it tells us, it answers the first question. So a class H is PAC learnable if and only if it has a finite VC dimension. Right, so there is this dimension, which I will define soon. There is a parameter assigned to every class, and if this number is finite, then the class is learnable. And if it's not finite, then the class is not learnable. And moreover, so before I tell you what the VC dimension is, I want to say one more thing. It also tells us what the optimal rate is. So the optimal rate is D over M, right? So the best algorithm, the best learning algorithm will misclassify the test point with probability VC dimension over the size of the training set, or proportional to that. Okay? So it really answers fully both the question of qualitative learnability and quantitative learnability. Now let me define the VC dimension, and I'm defining it because later we'll extend it to a more general context. So the VC dimension of a class H, of a class of binary functions H, is the maximum D, such that there are D points in the domain, x1 up to xd, And when you project, when you restrict all your functions to these D points, right? So you look at this pattern for every function in your class, then you see the entire binary hypercube. Okay, when you restrict your function class to these D points, then you see every possible binary pattern there is. Okay, good. So we answered the first question. Before that, let me also mention one more thing: is that the lower bound here is pretty standard. I would say it's like an exercise. So how does it work? So you pick the marginal distribution P to be uniform over a shattered set. And you pick the target function uniformly at random out of all the 2 to the D possible patterns on this shattered set, right? So we pick it uniformly at random. And then notice that if the algorithm sees only D over T examples, then the test point on which it will be asked, with probability at least half, it won't belong to the training set. It will be some point that it hasn't seen yet. And on this event, when the test point hasn't seen yet, because 8 star is a random function, the error the algorithm is going to make is 1/2. Right? No matter what it says, this random bit, the label of this new test point is going to be 0 or 1, probability 1/2. Right? So altogether, if we get D over 2 examples, any algorithm has error at least 1/4. And therefore, if the VC dimension is unbounded, then learning is impossible. If you have larger and larger shattered sets, learning is impossible. The upper bound is much more interesting, and it relies on the celebrated symmetrization technique by Vapnik and Chervonenkis. And I will not get into it now, but let me just mention that it underlies fruitful connections with other fields, both in TCS and mathematics. So it's really a very clever idea. Okay, so we answered the first question of what is learnable. What about the second question? How do we learn? Okay, so we know that every VC class is learnable, but what kind of learning rules are going to learn, to be sound learners? So it turns out that there is a very simple principle. All you need to do is to find some hypothesis which is consistent with the training data, and then you just use it to predict the test on the label of the test point. And this algorithmic principle, which is called empirical risk minimization, because you just find an hypothesis that minimizes the empirical risk, namely achieves 0 error on the training set. This follows from the theorem, the uniform convergence theorem, which gives you actually much more information. What it tells you is that if the VC dimension of the class is D, then with high probability, the following holds. Every function in the class, if you look at the empirical loss, how many examples it misclassified on the training set, and the population loss, the probability that it will misclassify a future point, those things are roughly the same. Namely, the difference between them goes to 0 with M. So this tells you that what you see on the training set is what you get on the test. And this tells you that if you pick a function with low error on the training set, then it will likely be a good classification rule on the test point. Any questions? Okay, good. So the take-home algorithmic principle here is that it reduces generalization to optimization. If we want to learn in this PAC learning, in the binary classification, all we need to do is to find a function in the class which minimizes the training error. This is very compelling, very simple. Okay, so now let's talk about the main subject of this work, which is multi-class classification. So multi-class classification is very similar, only that we no longer assume that we just have two labels. We don't classify images of cats and dogs, but we classify, maybe we get an image of an animal, and we want to classify to predict which animal it is, classify which animal it is, right? So it could be that the training set looks like that, and then we get a new example, and we need to classify it correctly. So here it may be a little bit strange because this test example is not even in the training set. But in general, imagine that the algorithm gets many images, and then a new image of some animal that has been encountered. Okay, so the definition is really the same, right? So you're given a training set and some labeled sampled ID and labeled by A star. And there is another point that is sampled from the same distribution, but it's unlabeled. You need to predict it correctly. There is some known class of functions, h from x to y. Now, y is not just two labeled, it has many labels. And the target function is from this class, but it's unknown. And the class h is learnable if there is a vanishing bound on the error rate of some learning rule. Right, so this is really the same definition. All we did is we replaced the binary label set by an arbitrary one. Okay, good. Again, so we can ask ourselves, which hypothesis classes are learnable and how, right? This is the same basic question from before. But it turns out that the answer here is not so simple. So let me tell you a little bit about the history of this problem. So like at the late 80s, like 35 years ago, Natarajan, and also with joint work between Natarajan and Tadepali, they initiated the study of multi-class PAC learning. So they were the first to study it in the West after Vapnik introduced it in the beginning of the 80s. And they identified two key combinatorial dimensions, two, if you will, two extensions of the visit dimension, which I will tell you about them soon. One of them is called the graph dimension, and this is a sufficient condition for learnability. So this dimension naturally arises when you take the upper bound, the proof from the binary case, and you try to extend it to the multi-class case. That's what you get. And the Natarajan dimension, which is a necessary condition for learnability. And the Natarajan dimension naturally arises when you extend the lower bound proof, this simple proof that we discussed earlier. Okay. So let me now define these dimensions. So let's begin with the Natarajan dimension. So remember, now we have a class of functions from x to y, and I want to define now when is a set of points x1 up to xd is Natarajan shattered by the class H. Okay, so x1 up to xd are shattered if there are d pairs of labels, ai, bi, right? So we have d pairs of distinct labels, right? Such that, again, we look at all the projections of all the class on these d points, right? So we restrict every function on the class on these d points. And what we want to see among these projections is the Cartesian product of these d pairs of labels. Right, so if you think about it, if we would write ai equals 0 and bi equals 1 for every I, we would just get, again, the binary cube. But now we don't have just 0 and 1. We have two labels for the first coordinate, two more labels for the second coordinate, two more labels for the third coordinate, and so on and so forth. But still, what you have here is something, it is a copy of the binary cube. Just, right, it's really an explicit embedding of the binary cube in this larger label space. Okay, is this clear? And the definition of the Natarajan dimension is the size of the largest subset, which is Natarajan shattered. So, or we can, in other words, we can say it is the largest D, such that the class H projects onto a D-dimensional hypercube, D-dimensional binary hypercube. Right? We project onto X1 up to XD, and we see the hypercube. Okay, and you can see that finite Natarajan dimension is a necessary condition for PAC learnability by the very same argument we sketched earlier. Right? You take a uniform distribution over the Natarajan shattered set, and you pick one of the 2 to the D many functions to be your labeling function, and you repeat the same argument exactly. Okay, so this is the necessary condition. What about the sufficient one? So this is called the graph dimension. And the graph dimension of H actually is reducible to the vis dimension of some class of sets. So what is the graph dimension of H? It is the vis dimension of the graphs of functions in H, right? So for every function H, you can look at the graph of the function. It's just the collection of all ordered pairs X, H of X. So it's a set of pairs, a set of ordered pairs. And you think about this as a family of subsets. And you look at the vis dimension of the resulting family of subsets. So by this interpretation, or by this definition, it's not so hard to see that finite graph dimension is sufficient for PAC learnability, because you automatically get this uniform convergence property that we discussed earlier that implied the empirical risk minimization principle. Okay. So what do we know? So we know that the optimal learning rate of a class is between the graph dimension over M and the Natarajan dimension over M. Okay, we have a lower bound and an upper bound, but these are 2 different dimensions. Okay, so Natarajan, he also showed that these 2 combinatorial dimensions are related, can be related. How? So it is not so hard to see, it's a simple exercise. You just need to digest the definitions, that the Natarajan dimension is at most the graph dimension. But it turns out also that in the other direction, the graph dimension is at most the Natarajan dimension times log size of the label space. So this, as a corollary, it gives us the following theorem. If the label space Y is bounded, then a class is PAC learnable if and only if the Natarajan dimension is finite, and if and only if the graph dimension is finite. So both of them characterize learnability when the label space is bounded. What about unbounded label space? So Natarajan, already in one of the earliest papers, he noticed that the graph dimension ceases to characterize learnability when the label space is unbounded. So he demonstrated a class H, which is defined in a geometric setting, which is learnable, very easily learnable. But on the other hand, the graph dimension of it is infinite. It's unbounded. So the graph dimension does not characterize learnability. And furthermore, he identified that uniform convergence in general cannot explain learnability when in the unbounded case. And this became more interesting in the recent years, and I'll soon tell you about the works of Daniely, Shalev-Shwartz, and Sabato and Ben David. This became interesting in the recent years because also in practice, we see that uniform convergence does not explain learnability, so it resembles it. So Natarajan left the following question open. Is it the case that the Natarajan dimension characterizes learnability even for unbounded label space? And Spoiler is the answer is no. We will discuss it later at the end of the talk. Any questions so far? Okay, great. So, okay, so we kind of answered how to learn when the label space is bounded. When the label space is unbounded, we still didn't answer that. But how to learn? What are the guiding principles, the algorithmic principles of learning? So as we said, when the graph dimension is finite, then actually you have a uniform convergence, and then you can just apply any ERM like before. Just pick a function which is consistent with the training set and use it to predict the test point. And you're going to be not so bad by doing so. But the situation is much more interesting when the graph dimension is unbounded. So as we said, uniform convergence doesn't hold. Natarajan showed it. Later, and more recently, much more recently, Daniely-Shwartz, Shalev-Shwartz, and Ben David, I think this covers all the authors here, show that empirical risk minimization doesn't apply. Right, so you could imagine situations in which you have no uniform convergence, but still empirical risk minimization applies. And they even show that proper learning doesn't apply. Proper learning means that the functions you use to predict the test point is from the class. You pick a function from the class and use it as a classification rule, as a prediction rule. So there are some classes that can only be learned improperly, so you really have to pick a function outside the class. And this follows by a nice Cantor-like diagonalization argument due to Daniely and Shalev-Shwartz. It's a very nice idea. Okay, so the situation, as we see, is very mysterious here, right? So the natural suspects don't work. So what does work? That's a good question that we still don't have a very good answer to. But it was studied in depth by this group, and it led Daniely and Shalev-Shwartz to introduce a new combinatorial dimension, which we called the Daniely-Shalev-Shwartz dimension, and I'm going to define next. Okay. Okay, great. So so this is now the first main result of this paper is that the multiclass learnability is characterized by the Daniely-Shwartz dimension. So let us first define the Daniely-Shwartz dimension. Okay, so the key combinatorial object that is relevant here, we call it a pseudo-cube. Let me define that. So imagine you have a set of vectors of B in Y to the D, right? So you look at all possible, Y is the set of labels, and you look at words of length D or vectors of length D, where every coordinate is a label from Y. So we say that B is a pseudo-cube if, first of all, there is a technical condition, we want B to be finite. And then the interesting property is that we want that for every vector in B and every index, every coordinate I, there will be another vector in B which disagrees. U and V, they disagree on the ith coordinate, but they have to agree everywhere else on all the remaining D-1 coordinates. Right, so the slogan is that every vector in B has a neighbor in B in every direction. Right, the direction is I, and so you see that the binary cube has this property, right? Right, so okay, so examples, so the binary, the Boolean cube is a pseudo-cube. This is clear. Natarajan cubes are also pseudo-cubes, right? These Cartesian products of pairs, right? And as we said, it's in a sense, it's isomorphic to 0, 1 to the D. It's the same kind of pseudo-cube. Here's another pseudo-cube, which is a bit more interesting. So imagine we have this this graph, this cycle, and notice that this graph is bipartite. It's an even cycle, so we have the blue vertices is one side and the red vertices are the other side. So look at all ordered pairs where the first guy is blue, second guy is red, and they correspond to the edges of this cycle, right? And you can see, okay, clearly it's finite, and you can see that for every pair 2, 3, there is a neighbor, right? So we can fix 2 and go to this edge. So, and then we have 2, 1 is also a legal pair. But we can also fix 3 and look at the 4, 3. It's also a legal edge. So there is, in this case, exactly one neighbor in every direction. So this is even a pseudo-cube where you have exactly one neighbor in every direction. It's most similar to the binary hypercube. Okay, any questions? Good. So the Daniely-Shwartz dimension is simply the largest D for which there exists a set of D points such that the projections of the class on these D points contain a pseudo-cube. Okay? Great. And it's not hard to see that the DS dimension is sandwiched between the Natarajan dimension and the graph dimension. I will not reason about it, but it's really not hard. You just need to digest the definitions and meditate a little bit. Okay. Okay, so the main result, or the first main result from our paper, is that finite DS dimension characterizes PAC learnability, even if the label space is unbounded, infinite even. And we also give bounds on the optimal learning rate. So we know that the optimal learning rate is between D over M, and this was actually shown in the paper that introduced this dimension by Daniely and Shalev-Shwartz. And what we showed is that it is at most roughly D to the 1.5 over M. So it's still open to get tight bounds on the rate. It could be, I conjecture it's probably D over M, but we thought about it, and yeah, this is the best we could do. Okay. So we answered the first question, what is learnable? Now there is a second question, how to learn. Maybe now when we have this new characterization, we have a better answer. So unfortunately, no, we still don't have a simple universal principle like ERM for binary classification. We don't, it's very interesting. But our upper bound involves a variety of algorithmic ideas. Some of them are classical techniques, including boosting, sample compression, transactive learning, and even empirical risk minimization is hiding there, at least in the analysis, and others. But we also introduce some techniques that, as far as we know, are novel, at least in theory. And most notably, we introduced the setting of least PAC learning. So let me tell you about this a little bit. Okay? Yes.
So I just have a question. So what do you mean by what else? What would be a simple universal principle aside from the proof that you guys give?
I don't know, maybe some regularization, you know, add the regularizer.
I see, okay,
and then do ERM or, you know, like in, so.
I see, you mean like a simplification, like a simple algorithm?
You know, like, you know, ERM tells you you just need in your class to find a function which minimizes the empirical loss, right? That's it. Find a consistent function in your class and you're happy. Maybe now you want to find a consistent function, but subject to some other cost function, which is reasonable, intuitive. So this is regularized empirical risk minimization. It's called in the machine learning jargon. maybe something like that. I don't think this will work here, but this would be like another algorithmic principle. Okay. Okay, so let me tell you about PAC Learning. So PAC Learning is very similar to PAC Learning, only that the learner has an advantage. The learner does not need to to exactly identify the correct label. It is allowed to give a short list of labels, and the goal is that the correct label will be contained in this short list. Right, so usually the size of the list should be much smaller than the set of all possible labels. Right, so here the set of all possible labels is all animals. I don't know how many are there, hundreds. And here we consider a list of size 3. Okay, so let's here is some inspiration from practice. So when you listen to YouTube, usually it will propose to you a list of songs to listen after whatever you listen to. And this is a form of list learning, right? So YouTube has they process your data, whatever you heard in the history, whatever they know about you, and based on your data, they give you a short list of songs, and they hope that one of them you will like and you will click on it. And there are other examples, like you can imagine. In medical applications, maybe you have an automatic assistant that gives a short list of diagnoses for given the data of the patient. Or yeah. Anyways, it's quite intuitive, I think. So how do we define this PAC learning? So again, it's like PAC learning. We have some unknown target function from a known class. There is an unknown distribution. And now we have this list parameter, which is, it is between 1 and the size of the label space. But we think about it that the list parameter is much smaller than the size of the label space. And then you're given, again, a training set of examples, of labeled examples, and another fresh test example. And your goal is now to output a list of size L such that the test label will belong to this list. And we say that a class is list PAC learnable with parameter L if, again, there is a vanishing bound on the error rate and the least learning rule that with probability at least R of M, if we do this experiment, at most R of M, it will miss. Right? With good probability, the list will contain the test label. Okay, so a very rough overview of the upper bound, which actually shoves under the carpet many of the I don't know, technical subtleties. But still, let me give it to you. So what we show is that from the assumption that the DS dimension is bounded, we can get a least learner. And then the least learner, we intuitively use it to reduce the number of labels from infinite, from unbounded, to L. And L is small. And once the number of labels is small, then we already know by Natarajan and Tadepali that you can learn it. You can, in principle, apply any ERM even and learn it because the graph dimension is small. So this is a lie what I just said, but that's first zero order approximation of the proof. And as I said, there are many other technical tools here, and I think it's really a nice proof to study because it involves a lot of classical techniques also. So okay, good. Okay, but what about the Natarajan dimension, right? So good, we characterized PAC learnability in the multiclass setting. We know it's the Daniely-Shwartz dimension. We know the graph dimension is not the right answer, but what about the Natarajan dimension? This was the main open question that Natarajan left. Yeah, so, and this question has been studied by many works in every decade since the 80s. So now I'm going to explain how we showed that the Natarajan dimension does not characterize multi-class learning. Eric, how much time do I still have?
So yeah, I think you have time. I mean, generally, yeah, it should be fine.
Okay, good, great. I think I need like 10 more minutes probably, and
yeah,
okay,
I think
good.
That's totally fine.
Great. Okay. So this is the key theorem that we proved. For every integer d, there exists a pseudo-cube with d coordinates in y to the d, whose Natarajan dimension is 1. Okay, so corollary is that there exists a non-learnable class with Natarajan dimension 1. Right, you just glue together all these pseudo-cubes, and then the ds dimension is going to be arbitrarily large, unbounded, because for every d, this gluing will contain a pseudo-cube of dimension d. So, and we know that the ds dimension, which is the size of the largest pseudo-cube, characterizes learnability. So it's not learnable by the previous result. However, the Natarajan dimension of all of these classes is 1. So we have a non-learnable class whose Natarajan dimension is 1. So Natarajan dimension does not characterize learnability. And this theorem, the way we prove it, we basically reduce it to a very involved construction in geometric group theory. By Januszkiewicz and Kwiatkowski. And these guys, what they proved, so they constructed a topological object, which is called the hyperbolic pseudomanifold. And what I'm going to do next is explain this object in combinatorial terms. Any questions? Okay, great. So let's, as a warm-up, let me explain to you how two-dimensional pseudocubes correspond to bipartite graphs. So imagine we have a bipartite graph with sides R and L, and define the following set of vectors. All the pairs U, V, where U is in R and V is in L, and U, V is in E. Okay, so it's all pairs that correspond to edges in the bipartite graph. Observe that B is a pseudocube exactly when G has no leaves, right? When every edge can be flipped, you can fix one end of the edge and move to another edge while keeping the second vertex. G is a pseudocube, so it translates to a very simple condition in the language of graph theory, that the bipartite graph has no leaves. And also observe that the Natarajan dimension of B is smaller than 2, if and only if G has no K22, no complete bipartite on 2 by 2 each side of size 2, right? If you think about it, a Natarajan cube, right? What does it mean? You have two symbols on the first coordinate and two symbols on the second coordinate, and you have all possible options, right? So you have two vertices here, and all possible edges between them. This is K22, and K22 is just a square, right? So really, the Natarajan dimension is less than 2, if and only if G has no squares. And here's an example for such a graph. It's the same example from before, right? So this is a cycle of length 6, so it has no squares. Length 6, and it's a cycle, so it has no leaves. And we already convinced ourselves before that this is indeed a kosher pseudocube. And now we also see that the Natarajan dimension here is 1. So the idea is to just take this simple observation and generalize it to hypergraphs. Okay, so let's do it. So let H be a D-uniform hypergraph. D-uniform means that all edges are of size D. So edges are no longer pairs, but they are D subsets of vertices. So we say that H is Bipartite, or if you will, D-colorable, if you can present the vertex set as the union of D parts, this joint union of D parts, V1, V2 up to VD, and each edge contains precisely one vertex from every part. Right, so this is just a generalization of bipartite graphs to hypergraphs. Okay. Now this topological word or concept, pseudo-manifold, what does it mean combinatorially? So H, the hypergraph, a D-uniform hypergraph H is called a pseudo-manifold if for every edge, every hyperedge in H, and every vertex that belongs to this hyperedge, there is another edge that disagrees with the first edge only on that vertex, right? So E minus E prime is a set contains exactly V. The only vertex that is in E but not in E prime is V. So E prime has another vertex because it has size D, which is not V. And notice how similar this is to this property that defines pseudo-cubes, right? That for every vector in every direction, there is a neighbor. This is exactly that. And now the claim is that if H is a D-uniform hypergraph and you define B like before, just you list all vertices in that are edges, then this B will be a pseudo-cube with Natarajan dimension 1, if and only if, actually you can strengthen it, the following condition holds. So H needs to be Bipartite. H needs to be a pseudo-manifold. So these two items together implies that you really have a pseudo-cube. The manifold, right, the pseudo-manifold property, we said it corresponds to a pseudo-cube. And then the Natarajan dimension 1 corresponds to the following property. So you want it for every pair of parts, Vi and Vj. If you look at the bipartite graph induced on Vi union Vj, right, you just look at the graph, the regular graph, you know, the standard graph between these two parts, right? So you connect a vertex here with a vertex here by an edge, if there exists a hyperedge that connects them in H. So this induced bipartite graph has no 4 cycles, just like before, has no K22. That's it. That's what you need. Here is the example we had from before, 2-dimensional case. Right, so we have the 2 parts, and here's another example which is inspired by topology. So right, so these arrows means that you actually identify this edge with this edge, you glue them together, and you identify this edge with this edge, and the bottom edge with the up edge. Right, and the hyper edges, the triplets that form edges here are all triangles. And you see the 3 parts. This is according to the shape and color. And you can see that this is indeed a manifold, right? Because if I want, so I have this hyper edge. Do you see my cursor, by the way, or am I just okay, good.
No, we see.
So we have oh, sorry. So we have, let's say, this hyper edge, this triangle here, and let's say we want to keep these 2 guys, but flip that guy, right? So we can go here. and go to the bottom triangle. And you can do it for any triangle in this picture, even on the boundary, right? Because this one, you can actually flip it to this guy here, because they're connected. Good. So actually, what these Polish mathematicians proved, so they constructed an H which satisfies item 2 and has no 4 cycles at all. Right, so they actually didn't really care about the bipartiteness, the colorability. What they constructed, or the theorem statement at least, didn't care about the bipartiteness. They just wanted to have no induced 4 cycles whatsoever. But luckily for us, bipartiteness was naturally implied by their construction. Good. So now the last thing I want to tell you.
Sorry, Shay. Is the bipartiteness important to like put these into coordinates to have like a natural order?
Exactly.
Okay.
Exactly. Precisely. So yeah, there's one last thing that I wasn't sure I wanted to say, but let me say it anyways. Because really, as I said, what these guys their construction is group theoretic. So it's really the hypergraph they define is based on groups and cosets, and they want to just state one statement in the language of group theory, which is suffices for our needs, and who knows, might have a simpler proof. So it suffices, but they get more than just the statement. So let me say it. So I need the following definition, which I think is quite natural. So imagine you have a group G, and you have 2 subgroups, U and V. So U and V are subgroups of G. That's how you denote subgroups in mathematics. That's what equal to. So we say that these 2 subgroups minimally commute if the following holds. You look at all products, small u times small v, where small u is from big U and small v is from capital V. And you intersect it with all products in the reverse direction. So you multiply small v with small u, where small v is from capital V and small u is from capital U. And you want that the intersection of these 2 sets will be exactly the intersection of the groups. Right, so notice that V intersection U, all the elements that are both in V and U, they are naturally in both of these sets. So this containment, you see this direction always holds. So we say that they minimally commute if nothing else is being added to this intersection. They commute as minimally as possible. And what we really need for getting these pseudo-cubes is the following. You want to prove that for every D, there exists a group G along with subgroups H1 up to HD. So H1 up to HD, these are subgroups of G. We want that every pair of subgroups HI and HJ will commute minimally. And you also want that the 2 to the D different subgroups obtained by taking all possible intersections of the HIs, right? So for every subset of the HIs, you can look at their intersections. You have 2 to the D options, 2 to the D ways in choosing a subset, such an intersection. So you want all of them to be distinct, right? So the HIs should really generate a lot of elements. Yeah, and the last item is that G is finite. That's what we need. We want a finite group and D subgroups of it, that every pair minimally commute, and the 2 to the D possible subgroups obtained by intersections are all distinct. Yes, and so okay, so that's it with the lower bound. Let me one last thing. Notice that if we omit item 3, if we don't require finiteness, then you can just take the free group generated by G1 up to GD. What is the free group? You just take all finite words in these symbols. And you can multiply words by concatenating them. And so this is an infinite group. Even when you just have 2 letters, you already get all possible binary words. So it's not hard to see that if finiteness is not required, and you take G to be the free group generated by D elements, and each HI to be the subgroup that is generated by all generators except GI, then you can show that this satisfies item 1 and 2. Every HI and HJ minimally commute, and the two to these subgroups are distinct. The highly non-trivial part in their analysis and construction is to basically take a quotient of the free group, which retains item 1 and 2, while obtaining finiteness. Okay, let me conclude with some suggestions to future research. So first of all, tight bounds are still missing. Then this construction of Natarajan, this lower bound is to simplify it, because currently it's really, even I have some colleagues that are in this area of geometric group theory, and even they told me that this construction of that we used is highly non-trivial. So even for people who are from the area, it's not a simple result. Another interesting direction that we're already studying, in fact, is list learning, right? So here in this work, it was just a mean to prove our theorem, but it can also be studied as an end. It's an interesting concept that is even used. And also combinatorially, to just study pseudo-cubes combinatorially, right? So these are interesting objects that resemble the binary hypercubes and seem to have many mysterious properties. And yeah, that's it. Thank you. So I did take more time than.
It's okay. Okay, so let me, thanks again, Shay, for a wonderful talk. I'll take us off the recording and we can just kind of stay and hang out and ask questions.